Okay, welcome to the next class. Alright, so we discussed that optimal operation of this process corresponds to what active constraints? It corresponds to V reactor at max. At low throughputs, it corresponds to V reactor at max, V stripper at max, X composition of the C leaking down the bottoms of column 2 is equal to, I do not know, something reasonable, maybe 0.5%. What we did was said was 5% is reasonable, let us just say some reasonable value. So, 1, 2, 3, and of course, we also had, what did we have, X D in the distillate plus X B in the distillate of column 2 should be exactly equal to 0.1%. Okay. Feed rate of A. So, 5 things are taken care of. Okay. I am left with 2 unconstrained degrees of freedom, and what we said was those 2 unconstrained degrees of freedom are reactor temperature and B composition in the reactor, right. Now, I know V reactor should be at max. Now, you see, okay. Now, let us say V reactor is not at max, max value is 80%, I am operating at 75%. My objective function would take a hit because I am not operating at maximum. Similarly, V stripper should be at maximum, my objective function again takes a hit if I am not at maximum. Yeah. Do you think the hit will be the same if I back off 5% from V reactor max and if I back off 5% from V stripper max? Do you think the loss in objective function, the loss in profit or loss in production or loss in revenue will be the same? Exactly. So, you see, economically speaking, a back off in some of the constraints will be much more than a back off in other constraints. Yes or no? And let us say for the time being that V stripper max is economically dominant. If it is economically dominant, what that means is if you back off from V stripper by even 1%, your economic objective function takes the largest hit. Your economic loss is the largest, your sensitivity of the objective function to a back off in V stripper is maximum. Let us just say for the sake of argument. Now, I want to draw a control system given that these constraints are active. I have also told you that as I start jacking up the production, because the instruction has come that maximize production, second column boil up becomes max. Yeah, we will do that transition later, but since I know that second column boil up is going to become max. Okay, so, as I transition V column becomes max at as throughput is increased. Yes or no? All right. We have agreed on this was done last time. This was the problem that we were trying to. Now that I know that V column is going to be at max, V stripper is going to be at max, V column can go to max if I need to jack up my throughput. Okay. I will start doing things. Let us say through choice of throughput manipulator is mine. Simplest thing to do is use the last constraint that becomes active as the throughput manipulator. You see, because that is the last constraint to become active, you can reduce the throughput by reducing it, and if you want to go to max production, you just max it. That is like pressing on the gas pedal in a car. Drive at maximum speed, you just press the gas pedal. Operate at max production, throughput manipulator is maxed out. So, then the most appropriate thing to do would be, from the point of view of not having to, from the point of view of having a single gas pedal, You want to max production, that throughput manipulator is maxed out, you are at max production. Okay. If it turns out that the economic hit because of a back off in that throughput manipulator, or that because of the back off in that last constraint to become active is also very large, then it is a very nice choice. This is the last constraint to become active, and a back off from this hits me economically the most. Okay. Then I say, okay, the throughput manipulator has to be there. Then what I have is a single gas pedal gives me low production, intermediate production, high production, max production. Okay. So, let us just start doing things, and I'll talk about it as to what I am doing. So, I know that this guy is going to become max. I do not want a back off here. Okay. So, I say, well, let us flow control it. Ordinarily, what would I do by adjusting the steam? Temperature or level. In this case, because D rate is very small, I will control the level using steam and temperature using the bottoms rate. But I know this is going to become maximum. If I am controlling level using it, using the steam, or maybe even a temperature using the steam, then what happens? Temperature controller requires some variability in the manipulated variable, guaranteed you will need some back off. Because of that back off, guaranteed you will be losing some revenue, or your objective function would be slightly lower than what it could have been. Yeah. So, therefore, the best thing to do is, because this is going to become active, I say that do not use it for control. Okay. Just hold it there. Similarly, this is something that is going to be active. Yeah. So, I flow control it. Conventionally, I will use this steam for temperature control in the stripper, so that benzene does not leak down the bottoms. Yes or no? If I am using it for temperature control, then what happens? Steam is varying to hold temperature constant. Therefore, I need a back off from the maximum amount of boil up. Yeah. I take an economic hit. Now, because it is an active constraint, it is telling me do not use this for control. If I did not know this is an active constraint, I would have conventionally just put a temperature controller there that is adjusting the steam. Yes or no? Because I know it is an active constraint, I leave it alone. If I leave it alone, it can be maxed out. Yes or no? No back off. Does that make sense or no? Ganesh, it does not make any sense to you. Huh? Then you say no, the mundi हिलाओ ऐसे करके, ऐसे करते हो तुम. Huh? Why does it not make sense? See, my constraint value on boil up is this. Okay. If I am using the boil up for controlling something, whether it is a level or whether it is a column tray temperature, what that means is boil up will have to move to control the tray temperature, right? Yes or no? It cannot be constant, because feed composition is changing, there are disturbances coming, the boiler pressure is changing, etc., 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 right. That being the case, feed to the column, the temperature of the feed to the column is changing, etc., 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 right. That being the case, my boil up is varying. We have discussed this before. If my boil up is varying, what is this? My boil up cannot exceed that black straight line. This is lost production, right, or this is lost whatever, lost revenue. So, I am operating on average at this level, which is let us say 95%. My optimizer is saying I want to operate at 100%. Because of variability in the boil up, I am forced to operate only at 95%, where I was capable of operating at 100%, because 100% limit can never be violated, it is a hard constraint. If the boil up exceeds this value, column floods, you need to take a shutdown, or you need to do other things, overrides come into play, right. That in itself screws up my economics.
By choosing flow controller here, basically we want to ensure the valve is open to the maximum.
No, it is not valve is open to the maximum. I think I drew it improperly. What I am doing is the following. Just a sec. Hang on. I am manipulating the steam to hold the boil up constant. Okay, since the boil up is the constraint, I am manipulating the steam to hold the boil up constant. Does this make sense? Okay. Now, you notice that the manipulation handle for the boil up to maintain boil up is right there. Yeah. So, this controller will be really tight. If this controller is really tight, then my boil up will be almost constant all the time, because the flow controller does not let it vary at all. See, temperature controller was deliberately varying it to hold temperature constant. Temperature can change because feed composition to the column has changed, temperature can change because the temperature of the feed to the column has changed, temperature can change because the reflux is slightly colder or hotter because the day is hotter or colder, it is day or night or whatever the hell, right. So, the point is, if I do it this way, the variability in the constraint variable is much less. Now, I am operating here, I am 5% away and I am not touching my 100% constraint, right. Then what I can do is, I can jack up and maybe I can operate at 99% without violating 100%. So, at the limit of flooding of the stripper or of the column. Yes or no, right. So, my optimizer is saying operate at 100%. If I am using the constraint variable for controlling something, maybe it is a level, maybe it is a temperature, maybe it is whatever. If I am manipulating it, I need extra back off, right, because it is an active constraint. I said do not use this for controlling anything, hold it right there, right. If you hold it right there, you can go closer to your max limit, yes or no. The closer you are to your max limit, the better economics or better whatever objective function you have, you are better off that much, yes or no. Does this make sense? Therefore, I flow control this and I flow control that. I also know guaranteed that I want to produce product which is 99.9% pure, yeah, okay. So, what do I do? What color is this? Black, okay. What do? I do, maybe this is what I do. I control a stripping a rectifying tray temperature. I control a rectifying tray temperature using the reflux, okay, and this tray temperature set point is coming from a product quality measurement, product impurity measurement. So, if the impurity, what would CC, which component are you measuring? B, C, D, A, what? No. C? Why C?
Because they are B and D and A.
No. So, I think this is fundamental. What is this rectifying section doing?
Separating the concentration.
Yeah, of course, the column separates. What the hell is it separating? Well, B is the lightest component. Whatever B leaks down is bound to go into C. It is preventing D from leaking up the top. Yeah. So, by adjusting reflux, what are you going to control? Amount of D. Let us say you say no, I am going to control the mole fraction 99.9%. What is the problem with that? Is there a problem with that, or are the two things are equivalent? That is my next question. You see, the two are not equivalent. Why are they not equivalent? Suppose for some reason extra B leaks out the first column. You are saying 99.9% pure, adjust reflux to maintain purity at 99.9%, right. Let us say for whatever reason 1% B leaked down. No matter how much you change the reflux, you cannot go beyond 99%. You can do infinite reflux and still bloody it will be, right. Now, with that kind of a controller, you are seeking something that is not feasible. 99.9% with 1% B leaking in the first column or in the first stripper is simply not feasible, right. That controller is bound to do things that is a not well designed controller, not enough thought was put. Do you see what I am saying? Yes or no? You are saying 99.9%, here it is 99, whatever, 1% B is leaking down. No matter what you do, that controller is bound to fail. What will it do? It will just keep jacking up the reflux. Reflux will hit its max, or maybe the column will get flooded earlier because you are dumping so much liquid into the column, and then you will say, oh shit, this column is not doing its job. It is not this column, it is the previous column from where extra B leaked out, right. Your whole attention will be, oh, reflux has been increasing. Do you see what I am saying? Okay, so what subscript goes here is actually fundamental. The subscript here is D. Shit.
And don't we need to know the amount of B which has leaked?
Just a sec, we'll absolutely. Okay.
Sir, how can detect here B coming or not?
We'll do that, don't worry. Okay. How do we do it? Well, one by one. Okay, so you want to now detect B. How do you ensure B doesn't leak down the stripper? This is the stripper. How do you ensure that B does not leak down this stripper? Boil up is going to be active. I don't want to use it, because if I start manipulating the boil up to ensure B, then what will happen is the boil up will have to be 95%. It can never be 100%. You need that 5% so that temperature can be controlled, right? We just argued this out, this picture right here. Yes or no? So how do I control the temperature? I will control the temperature this way. If the temperature is going down, what does it mean? That means light stuff is leaking down, put in less feed. Yeah? If the temperature is increasing, that means light stuff going down is decreasing, increase the feed. Yeah? Will this be tight? Well, yeah. As long as the tray temperature is close to the feed, not exactly the feed, but maybe couple of trays or 3 trays below it, you change this, tray temperature will almost immediately change. Yes or no? Okay. So it is a reasonably fast loop, control will be tight. Yes or no? What does that do? That allows me to operate the stripper at max boil up. I can set this set point at max because my optimizer is saying so. Why do I set it at max? So that the recycle rate is max. If the recycle rate is max, my reactor is operating at as much excess A as possible, my side product is as little as possible. Yes or no? Okay. So okay. Now you are going to say, well, temperature doesn't exactly control composition, which is true. Okay. And since I want product quality, what I do is I measure, you see my lab will tell me how much B impurity is going in it too, right. And then what I will do is I will say, okay, if benzene is increasing, yeah, but temperature will ensure that much does not leak. Anyway, you are getting those composition measurements twice in a shift. So if after a shift you are saying, look, benzene is increasing, what will I do to the temperature set point? I will increase the temperature set point. That is something that the operator will do, but I am just showing it as a loop. If you have an online analyzer that is giving you a reading every 15 minutes, well, then this loop is, it is a PI loop or a PID loop which is doing a reasonably good job, right. You see, you cannot prevent this, it has to be this way.
Why can't you measure C? The same problem, because B will leak down and we would.
You see, it is for you to decide what you want to measure. Your measurement must be aligned with the function that the equipment is performing. The rectifying section, its equipment is to prevent D leakage up the top. The stripper, its function is to prevent B leakage up the top. You can keep measuring C and you won't know whether the equipment is performing its function or not. Do you see what I am saying? Understanding of the function is fundamental. If you don't understand the function, you can't do good control. You will do something that is bound to fail. It will not fail now, maybe 6 months from now it will fail, but it is bound to fail, because ultimately you ended up seeking something that was not realizable, not feasible. Okay. So, these subscripts are important. Just saying composition control does not cut any ice. Okay. Which composition, which component, why, must be understood. Okay. Then, well, so now we need, okay, so what have I done? I have a V reactor max. Well, level is something that's a controlled variable. You see, level needs to be controlled because it does not regulate itself, right. So, well, now you have already taken away this valve. Level cannot be controlled this way, it has to be controlled that way, yes or no. So, let us just say I am going to control the level this way, okay, and I am going to maintain A in ratio with B. So, there is a multiplier, there is a ratio set point that is close to 1 on a mole basis. Is it close to 1? Is it more than 1, less than 1, exactly 1? Why? Think about it. Well, A plus B goes to C, C plus B goes to D. Now tell me, is that ratio more than 1, exactly 1, less than 1? Yeah, so of course, much more than 1, 10, okay, 1.05, 1.2. I don't think you have understood anything. That is a sad commentary on what I have been teaching. Suppose there was no side reaction, fresh A to fresh B ratio should have been what? Exactly 1, right? Okay. There is very little side reaction.
It should be less than 1.
Yeah, why?
Because mole B.
Exactly, 2 moles of B are getting consumed to form 1 mole of D. Only 1 mole of A is getting consumed to form 1 mole of D. So, if you are forming 95 moles of A and maybe 5 moles of D, you can back calculate how much A was needed and how much B was needed. That will come from stoichiometry, right? And then if you take the ratio, slight extra B would be needed, but only slight. Why only slight? Because the amount of D is only very slight. That is 100, this is only 5. C is 100, this is only 5. Does this make sense or no? This is overall material balance. It has got nothing to do with control. Yes or no? Then how the hell am I having excess in the reactor? Recycle. You see, this recycle rate can be whatever. It could be 100, it could be 200. See, let us say fresh A is 100, B is, let us say 102, 103, because B has to be slightly more. Okay. Recycle could be whatever. It could be 0, it could be 50, it could be 60, it could be 100, it could be 200, it could be, I don't know, 300.
In recycle stream both A and A will be.
But you see, because A is the lighter component, see, this is, that is the problem.
We are losing B out here, so.
Okay, let us say B is extra in the recycle component stream. Okay. Let us say there is too much B, very little A in the recycle stream. Okay. Then what you are saying is, because recycle is large, I am having actually too much B and very little A. That is what you are saying, right? Okay. If that is the case, what will I do? I will change the ratio set point so that I start feeding extra A, less B. Okay. Where does the extra A go? It is not taken out, it has to go into the recycle. When I am putting in extra A and less B, that extra A is going in the recycle. Ultimately composition will come to mostly A, little B. Yes or no? Yes or no? Does this make sense or no?
Yes.
I am putting in exactly 1 mole of A, exactly 1 mole of B. In the reaction, extra B is getting consumed because some D gets formed. What will then happen? Recycle rate will continue to go down, and we will flip to what you are saying. To ensure that doesn't happen, I will put slightly whatever. My logic may have been flawed, but the basic point is you have to think of inventories. A and B are not being taken out in C and D.
So the excess point can be set by composition.
Exactly. So what we are doing is reactor composition of B. Why B? Because B is supposed to be the limiting reactant. Okay, you have too much A, so you want to detect what is the impurity, or not impurity, what is the limiting reactant. That is always usually the case. This is setting the ratio set point. Yeah, you can set this ratio set point at too much B, and then the ratio will get adjusted so that there is too much B in the recycle. You can set this composition set point as at very little B, let us say only 5% B inside the reactor, and then the ratio will get appropriately adjusted, whether you are putting in extra A or extra B, that will get automatically adjusted. Yes or no? This is inventory, this is ensuring that all component inventories are properly accounted for. So in this scheme, because B is going to be the limiting reactant, this ratio set point is going to be slightly less than 1.
So it may jump more than 1.
Well, in that case, well, if that happens, then the composition will start changing, because that is building up in the recycle loop, and when that composition starts changing, the composition controller will adjust the ratio set point automatically.
In the steady state it has to be less than 1.
In the steady state it has to be less than 1, exactly. How much less than 1, that is in your hands. 5%, 10%, maybe 30% is okay, that is a separate question. We are not addressing that question, but in terms of understanding all component inventories are properly accounted for, this is fundamental. We did this last time, we are doing it again. Okay, this is fundamental. Okay, now we start coming to whatever else, levels, pressures. Well, pressure control is this way. Of course, pressure control here is this way. Level control here is this way. Yeah, I have done CSTR level control, and I am going to say this guy is going to be, well, almost max but not max. Why almost max? Because level is always the controlled variable. So level cannot be held really tight, it will show some variability. So you will have to back off a little bit no matter what, because it is a controlled variable, it is not a direct manipulated variable. Okay. Okay, so level is near max. Yeah. Well, what else? What other levels and pressures do we need to control? Second column level. Well, available handle is here. Oh shit, then how do we control the level here? That is not a good idea. Well, that can't be done. You see, then how do I control the level here? So I control the level here using this.
You will not touch the D flow rate, right?
Huh? No, we will touch the D flow rate because it is important to ensure too much C does not leak down the bottoms. Okay, so there is a, for example, maybe a composition controller or a temperature controller that does this. Yeah. This is being done to ensure this constraint is met, because if too much C starts leaking down the bottoms, what am I doing? I am screwing myself again. Yes or no?
Yes.
Okay. Okay. I don't know if I have done everything. So now this level remains. How the hell do I control this level? You can't not control it. By the way, what is accumulating at the bottom of this column? C and D. Where are C and D getting produced? In the reactor, right? So if this level is going down, that means I need to jack up the generation rate, the reaction rate inside the reactor. By the way, of course, this will be temperature control, that's obvious, right? Yes or no?
So, in the second column, we are using temperature control twice, so we can.
No, we are not using temperature control twice. We are controlling temperature of the top section using reflux. We are controlling so that the amount of impurity going in the top, D impurity in the top is controlled, because that's my product. I also don't want too much C, which is the light key, going down the bottoms. What is the rectifying section doing? It's preventing the heavy key from going up the top. What is the stripping section doing? It's preventing the light key from going down the bottoms, right? These are two separate tasks, so I can control two temperatures. That's what I am doing. The line went away. It's some stripping tray, don't confuse. One tray in the above the feed, some tray below the feed. Okay, which tray is a separate matter, that's a subject in itself, we'll take care of that later, but the basic idea needs to be clear. Okay, so I cannot have this level floating, right? I need to control it. Yeah. Huh?
You have only one option.
What is the option? There are two options actually.
Temperature controller and this one.
Huh?
We have this temperature controller option.
Yeah, so I can manipulate the temperature set point, or I can manipulate the B composition set point, right? What would I do? I would say, well, to maintain this level, this is unconventional. Usually you are maintaining levels using flows, in flow, out flow, some kind of a flow. Here you are adjusting a temperature to, this is quite unconventional.
So that in this case, we will need to make sure that the set point which we are setting is not maxed out.
Okay, so what will happen is, when I receive the instruction from top that maximize production, okay,
We will still have to leave a little margin because the temperature.
yeah, temperature some margin, temperature will have to have some margin. Let us say this is my throughput manipulator. Let us say this, this guy is my throughput manipulator, so maybe I should show it in some other color. But this is the last constraint to become active. Let us say I am using this as my TPM. So the guy says jack up throughput to the max extent possible. What will I do? I will start increasing this set point. As I start increasing this set point, what will happen? Boil up has increased. If boil up has increased, level will start to go down because you are boiling off more stuff. So I will start sucking in more from the stripper. Level of the stripper will go down. Level is going down, so the stripper is saying jack up production. Level controller is saying jack up production, increase the temperature. Temperature increases. Okay, so level in the stripper starts to go down. The level controller increases the temperature set point inside the reactor. Because the temperature set point has increased, more consumption happens, more consumption of reactants happens, therefore more C and D are produced in the reactor. Therefore the feed to the stripper, which is the reactor effluent, this chap, this will be richer in the heavier components, C and D. Okay, heavier components will cause temperature to rise. If the temperature is rising, what do you need to do to the feed? The stripper temperature controller will say increase the reactor effluent flow rate. Reactor effluent flow rate increases, level starts to go down in the reactor, that starts sucking in more B. Level controller of the reactor starts sucking in more B. Ratio controller ensures that more A gets sucked in.
So
Yes.
Temperature controller is
Which temperature? There are many temperature controllers.
the stripper temperature
Huh.
controller. If we have more of C&D entering the stripping column,
Uh-huh.
the temperature would increase.
Yeah.
So how would that? How would that control the amount coming into the stripper?
Precisely. We discussed this. How does that temperature controller work? If the temperature is decreasing, that means lighter components are accumulating down. That means my boil up is not sufficient to send them up. That means I am putting in too much material into the column, so reduce the feed rate. That's how this temperature controller works, right? Now what's happening is, now we reverse the equation. More heavy material is coming in because the composition in the reactor has changed because of extra consumption, because the temperature has increased. So more C and D are coming into. Those C and D are designed to go down. As they are going down, the temperature will go up. If the temperature is going up, what will the controller do to the feed? It will say increase the feed, because, right. So as you are pulling in more feed from the reactor, level of the reactor goes down. You start pulling in more B. The level controller starts pulling in more B. Ratio controller makes sure that more A gets pulled in. If there is any mismatch, the composition controller takes care of that. CCB, this guy. If there is any mismatch in the fresh A and fresh B, composition controller will adjust the ratio, make minor correction to the ratio set point. Maybe it goes from 0.95 to 0.955 or 0.945 or whatever, so that any slight mismatch is properly accounted for. Does this make sense or no? Huh? Fine. So I start jacking up the throughput. I keep jacking it up, level controller keeps increasing the temperature of the reactor. Then finally what happens, this temperature reaches some max limit. I can't jack up the temperature any further because of whatever, some reason. Select, when an instruction comes that jack up production as much as you can, basically selectivity is not the primary concern. It is a concern, it shouldn't go down too much, so that you are producing more D than C. As long as D is the minor component, you are okay. Okay. So maybe selectivity goes down from 97% to 95% because you have jacked up the temperature. We argued this last time. If C is earning you so much premium because of something that happened in the market, you really don't care how much D you are producing, as long as, let us say, selectivity is greater than 90%.
So we didn't complete that discussion.
We didn't? I thought we did. Okay, doesn't matter. I think that's food for thought for you. Okay. Now the point is, when I'm increasing the throughput manipulator set point, which is the boil up in the second column, this temperature is bound to increase. Temperature in the reactor is bound to increase by the action of the stripper level controller. Yeah. Then temperature reaches maximum. What do I do? So then I say, well, temperature has reached max. This has now reached max, maybe slight back off. When I say max, if any back off is necessary, that back off is implied. Okay. Now what do? Level needs to be controlled. You see, I cannot have level floating, because then if level goes below 20%, I will have to shut down the process. Well, you see, we argued, I do this gets sucked in, that gets sucked in, that gets sucked in, ultimately more feed is getting sucked in. It has to happen automatically by the way you structured the control system. So what do I adjust now? I can't adjust temperature because it's at max. Then I say, okay, I can't increase production anymore. The question is, can I increase production further? Is there a degree of freedom that is left for me to manipulate? What can you adjust to increase the production of the compound in the reactor? Temperature you could have jacked up. What else could you have jacked up or down? Level is already at max. Heat flow rate. Well, feed flow rate is already under ratio control and level control. That's not in your hands. The fresh feeds are already under level control and ratio control, right? The way it is drawn there. Yes or no? उसको आप हिला नहीं सकते. Can you adjust something that indirectly adjusts the feed? Absolutely. There you go. Limiting reactant was 5%. Now I start jacking up its composition from 5% to 6%, 7%, 8%, 9%, 10%. More limiting reactant going in. You see the composition controller will adjust the ratio. If you adjust the ratio, you can always adjust the ratio in a manner so that more B gets sucked in. More B is getting sucked in, that means the composition of B in the reactor is increasing. If composition of B inside the reactor is increasing, well, reaction rates are K times XA XB, K times XB XC, right? Basically, you are producing more C and D. Yeah. So once you have lost that degree of freedom, I am starting to use my last remaining degree of freedom. Yeah. Yes or no? Okay. I keep now instruction from above is max it out. Drive the car at maximum throughput, maximum throttle. So you are supposed to press the gas to the end, right? So I keep increasing the throughput manipulator set point. Ultimately, what will happen? In response to this increase in throughput manipulator set point, my composition set point for B will keep going up, right, until throughput manipulator reaches max boil up. Yes or no?
The level controller was first directing the temperature set point.
So this is called split range control. So you got a controller, it's adjusting something. When this becomes saturated, it starts adjusting something else. This is called a split range controller. This you should have studied in undergraduate. If you have not, doesn't matter, we'll cover it, but not right now. Okay. So your level controller is essentially a split range controller. It's adjusting temperature. When temperature maxes out, it's adjusting the composition, reactor B composition. Does this make sense or no? Now notice that once this TPM reaches max, boil up cannot be increased anymore because the column is flooded. Whatever A is getting sucked in, whatever B is getting sucked in, well, your process is floating at whatever is the maximum throughput for this process. Does that? Yeah.
Wasn't boil up already at max?
No.
Okay, we decided.
We used it. We are using it as the throughput manipulator. Because it is the throughput manipulator, when this boil up reaches max, I can't, since boil up in the column is the last constraint to become active. It is the bottleneck constraint, right? Beyond this, throughput cannot be jacked up, right? You see, there are multiple constraints. Level is active, boil up in stripper is active, then temperature became active, product purities are also active, right? Finally, column became active. Column boil up became active. When it became active, throughput cannot be jacked up anymore. You have reached the maximum pedal. You can't press on the gas anymore. That's it. Right? Yes or no? It makes sense or no? Okay. So well, that's it. So now let me back off. Let me revise. When I am at low throughputs, temperature is in my hands. Let's just, so level control is like this. Yeah. What are the two things that are in my hands? I adjust the throughput manipulator so that I get whatever FA I want. You see, let's look at what is written in red. I adjust the throughput manipulator, and by adjusting the throughput manipulator, I essentially figure out, adjust what is, how much fresh A and fresh B are getting sucked in. We argued how that gets done. That this level goes down, that sucks in more from the previous unit, that level goes down, that sucks in more from the previous unit, until more A or less A as is necessary gets sucked in, more fresh A or fresh B gets sucked in. Yes or no? Right? So I can always adjust this throughput manipulator to get whatever FA I want. Yeah. If the FA is too much, reduce the steam set point. If the FA is too little, jack it up, right. I can always adjust it to get whatever FA I want, yes or no? Okay. V reactor max, well, that is coming from the set point here. This set point is kept at max. Second thing. V stripper max, well, it is already at max. Yeah. XBC2 is equal to 5%, that is being, I am adjusting this set point so that the amount of C leaking down here is about 5%. Okay. And last but not least, which is not being done, well, that is actually getting done. So, I say that okay, the amount of B leaking in the distillate, this guy, I set it at some value, and then this guy is 0.1 minus whatever this is. Well, I can't write it, but you know, this set point is a dependent variable.
But then again the issue is that
There is no issue.
greater than 0.1.
Yeah, so this will come out to be negative, and then your alarms will go up. How can you have a negative composition set point? That's just not possible. It can be 0.000001, but it cannot be minus point whatever. Right?
So alarms could offer not a problem. I mean,
Well, alarm, well, high level alarm, low level alarm, high temperature alarm, low temperature, these things keep going off and on, and operators do take appropriate action to adjust the problem. So, when if it is says this is going negative, operator knows, well, that means too much B is leaking out, that means I need to do something in the stripper, right. So, that takes care of that. What was I trying to say, man? I lost my chain of thought. Okay, what are the unconstrained? Everything is taken care of. The only independent things are what? This and this. We argued there is 2 degrees of freedom. You see, this guy, the TPM has been adjusted to get FA. This is really not a degree of freedom. It is not an unconstrained degree of freedom, right. We counted 1, 2, 3, 4, 5. 5 constraints are active, 2 things are left. That means the operator is free to set 2 things. What are those 2 things that he is setting? Composition of B in the reactor and the impurity B leaking down the bottoms. Once he sets that at some value less than 0.1, amount of D that is allowed to leak up the top is 0.1 minus that, right. The 2 independent things, degrees of freedom is fundamental. There is total 7 steady state degrees of freedom, 5 active constraints. That means operator is not free to adjust, 5 set points will get adjusted to drive those constraints, right. What remains, those are in the hands of the operator. Okay. Now, I am saying I want to jack up the production. Okay. So, what do? I start jacking up the production when temperature becomes max, this becomes max, then the level control has to be this way, composition is no longer in my hands. Do you realize the moment this moment temperature became max, I hit a constraint, I lost a degree of freedom, right. When you hit a constraint, you lose a degree of freedom. A degree of freedom is being used to drive the process to that constraint, right. What is left in my hands? Composition of B leaking down the bottoms, right. I can adjust this in that band of 0.1% from very small close to 0 to very close to 0.1%, but not beyond. Okay. If the objective is to maximize production, where would I rather keep this? As well as maintain quality, I would rather keep this B to be very small close to 0, because if too much leaks down, it is bound to contaminate my product. Also, the last constraint to become active is boil up in the second column, right. If I prevent B from leaking down the bottoms You see, the point that I am trying to make is XA plus this guy, the last constraint. I could have in my product large amount of B and very little D, such that they sum to 0.1%. Alternatively, I could have large amount of D and very little B. I could have both scenarios. The point is, that's in my hands. How is it in my hands? If I set the B set point, D set point is 0.1 minus that. Yes or no? Now, because the last constraint to become active is the boil up in the second column, I would like that boil up to get active as late as possible. How do you do that? By allowing as much. What is the second column doing? It's separating D and C. If I allow more impurity D in the top, my reflux goes down. If my reflux goes down, my boil up goes down. Yes or no? In a conventional sense, not in this control system, but in a conventional sense. So, from all these arguments, I can say that to maximize production, B should be in very small quantity, D should be the major impurity. Yes or no? Does that make sense? That will give me maximum production. If I do it the other way around, then this second constraint will become active earlier. Why will it become active earlier? Because it requires too much reflux. Yes or no? If it requires too much reflux because amount of D impurity is tight, then the boil up will have to be more, right? If the boil up is more, then it will get active earlier, throughput will suffer. Does this make sense or no? Right? So, I had two degrees of freedom left. 1 degree of freedom got lost when the temperature became maximum. 1 degree of freedom was still remaining, and I use that degree of freedom in a way so that I remain feasible, okay, and make sure that the boil up, which is the last constraint to become active, gets active as late as possible, because that is what gives me maximum production. Does this make sense or no? If it does, I think we have done sufficiently enough. Okay. Any questions? It sounds so easy, but man, when everything has to be thought through. The only problem that I see with this control system is that this level controller on the stripper is actually quite unconventional. Okay. Now, let us say your reactor is actually very big, its residence time is of the order of 2, 3, 4 hours. Then it may so happen that before the effect from the reactor could trickle down to the bottom of that column, the column bottom level has either hit 0% or whatever, 20% or 80%, the max and low limit. That can make this level controller fragile.
That's what I was saying earlier, we have to make sure.
Yeah. So, but if the residence time is not too much, let us say the residence time is, I don't know, maybe 10 minutes, this will work, no problem. It depends on the residence time. Yeah. If the reactor is really, really big, you do something, it will take a heck of a long time for the temperature to respond. It takes 1 hour for the temperature to respond. By that time, your stripper level has run dry or it has overflown, right? That is also not acceptable. In that case, we will have to redo something here. Okay. But the point is, conceptually, this is how I would rather do it. If it turns out that the level controller is fragile, I will have to give up on tight control of either boil up on the stripper or boil up on the second column. Something will have to be given up, because it is turning out that my level control is fragile. Does this make sense or no? Okay. We will take care of that maybe next time. If the reactor is not a CSTR, it is a plug flow reactor, well, there is no residence time, this will work, guaranteed it will work, no problem. Okay. The point is, to be able to come up with this kind of a scheme, figure out if the inventory control will not be too fragile. If it turns out that the inventory control, for example here the level controller on the stripper is turning out to be fragile, we will have to redo it, we will have to make some adjustments someplace, right. But if it turns out no, inventory control is also acceptable, this is perfectly okay. When will inventory control be acceptable? As long as the CSTR residence time is not too large. How large is too large? Well, that is a separate question, you can simulate and figure it out, okay.